Hi everyone, we're going to get this webinar started. This is Lad Keith with the University of Arizona. I'm an assistant professor in urban planning here, and this is the Extreme Heat Network's webinar series. The Extreme Heat Network emerged from a NOAA-funded regional integrated science assessment project here at Arizona called CLIMAS, where we were looking at how communities use urban heat island maps for decision making, and that's kind of emerged into this community of research and practice around extreme heat. And we're really excited to have Pete Aniello here with Trust for Public Land today. Just a couple of webinar logistics for everyone if you haven't joined us before. Reminders that we're using the freemium version of Zoom here, so please keep your webcams and microphones turned off. After the presentation by Pete, we'll have some time for questions and answers, but please send those to us via the Zoom chat box, and you can open that by pressing Alt and H, or it's at the bottom of your Zoom screen, and we'll moderate those questions, and as time allows, let Pete answer a couple of those at the end. And also, if you join us later on, or if you want to share this presentation, we have all of our recorded presentations at heat.arizona.edu, and those are posted on the YouTube channel, but you can link to those from our website. And with that, I'll turn it right over to Pete Aniello. Again, he is the Senior Manager for Science and Analytics at Trust for Public Land, and today he's going to be sharing some of their work on rapid production of urban heat island maps across the United States. So Pete, do you want to take it from here?
Sure, yeah. Thanks, Lad, and thanks everyone else for attending. As Lad said, I work at Trust for Public Land. I'm the Senior Manager for Science and Analytics. My background has been in the geospatial field for the last 30 plus years. I started out at what's now NGA, the National Geospatial Intelligence Agency, and did some stints at USGS and Esri, the geospatial software company. Most recently, before TPL, I was at Sandia National Laboratory here in Albuquerque. And so now I'm with TPL. And before we get started with the heat data, I'd like to just introduce you to TPL a little bit. So next slide, please. So TPL is all about protecting land. So we create parks and protect land for people. We've been around for 48 years, and we've got, our headquarters is in San Francisco, but we've got around 300 people in around 30 states. I'm a member of the GIS team, which we have 11 people located mostly in Santa Fe, New Mexico. Although that's our home office, 3 of us live in Albuquerque and commute up to Santa Fe just when we have meetings, and the rest of the time work from home. We also have one member, a cartographer, who works from her home in Flagstaff, Arizona. Next slide, please. So where do we work? Pretty much everywhere in the United States. So you can see the map. The blue dots are completed projects, and the black dots are TPL office locations. There's a few states that we haven't worked in yet, but as you can see, we've worked in the majority of the United States. Next slide, please. So more importantly, what do we do? Pretty much anything having to do with creating and protecting land. Pretty much like any project that we do is the goal is land for people. We protect land through private to public transactions through real estate and conservation easements. We maintain the National Conservation Easement database that you may have seen and is available online. We do park development and programming. And up to this point, we've protected over 3 million acres in 5,000 plus projects. Those are the blue dots that you saw. Obviously, the 3 million acres are not just dots. They range in size from small pocket parks on up to, I think the most recent thing we protected is what is going to become Fisher Peak State Park in southern Colorado, and that's about a 20,000 acre project. just north of the New Mexico border. So we work on a wide range of places. And we have our geospatial science team does all these things and more. So we identify parcels to get into the public realm. We're doing machine learning to identify park amenities so that we can figure out where people might be attracted to and what kind of programming might attract people to a local park, or what pulls them from farther away. We're doing demographics of public land users. So we've got anonymized cell data that we use to analyze and create maps of patterns of visitors of parks. We do recreation opportunity spectrum mapping. So this was originally a Forest Service product that we've modified somewhat so that it can be used anywhere, not just nationally. We do storm runoff predictions, and as this presentation indicates, heat island identification. And those are just some of the things. We do way more than that. In fact, we probably have, of course I'm biased, but I've been around for a long time in the geospatial business, and we probably have the most capable GIS team of any nonprofit that I've seen. Next slide, please. So why identify heat islands? So I'm sure pretty much everyone listening already knows of these reasons and a lot more, but I'll go ahead and go through them anyway. So excess heat causes health problems, especially among vulnerable populations. And according to the EPA, trees and other vegetation are the most effective mitigation for a heat island. Locating a park in a heat island reduces heat and adds recreation. So we're all about adding recreation, but where we can mitigate heat, we're also trying to do that. And it's possible, I don't know if there's any studies on this, but there's a theory that says mitigation of heat islands can help reduce use of air conditioning, which would help with climate change. Next slide, please. So I guess a better question is, why is TPL involved in heat islands? So we have a number of applications that we've incorporated heat into. One is ParkServe. So this is a public application that we've done geospatial analysis and presented it through a web mapping application that shows where parks are needed based on populations that don't have park access and the characteristics of those populations. We've got something called Climate Smart Cities. This is an application that we develop on a project basis. We have a template, and it identifies areas for heat reduction, stormwater runoff mitigation, recreation. It incorporates wildlife habitat, things like that. We've done Climate Smart Cities instances for New Orleans, Cleveland, LA, Boston, maybe a few others. There's something now called the Drawdown Initiative. Basically, how can cities contribute to climate change solutions? So it incorporates carbon and carbon storage, and we're building an app based on the Climate Smart Cities app that also includes a carbon storage measurement. We're doing that right now. We've just started for the city of Cleveland, and if that's successful, we plan on doing that in a lot more places. And then we're also interested in demographics. So where are disadvantaged populations disproportionately affected by heat? And as I think I mentioned, parks are potential mitigation for that. Next slide, please. So this is where it's gonna start to get technical. I've tried to keep it from getting too deep in the weeds, but it's some degree of technicality is kind of unavoidable. So please bear with me, and I'll be happy to answer all of your questions. So I'm going to step through each of these on different slides, but an overview is we take Landsat 8 satellite data. We access that through Descartes Labs platform. So Descartes Labs is a partner of ours. They're also located in Santa Fe. They're a spinoff from Los Alamos National Laboratory, and they have an extremely fast computing system and an API or application programming interface through which to access their data. We access their data by writing proprietary Python code that we run on their system. When we get results back, we bring that into ArcGIS Pro, which is geospatial software. We then take the data that we've gotten back and put that data into an image service, and that image service into ArcGIS Online, which is a spatial data sharing platform. So that's a super high level overview of the process. And so I'll start going through these step by step now. So next slide, please. So for those of you familiar with Landsat data, we're using band 10. That's the thermal data we're using, as band 11 has had some technical issues. Those may have been fixed by now. We may revisit using a combination of bands 10 and 11 in the future, but for right now, we're basing the heat island data on Landsat 8 band 10. I'll go over just satellite data in general here. And the thermal data is in the form of digital numbers. So it doesn't go along collecting temperatures. It collects what the sensor interprets from the temperature. And these are called digital numbers. And each pixel is assigned a digital number. And Landsat images every point on Earth with a revisit time of 16 days and at a resolution of 30 meters. So we need to grab these digital numbers and convert them to a number that we recognize as temperature. And since we produce this data for the US, we're doing it in degrees Fahrenheit. There's nothing preventing us from doing it in Celsius, but if the US audience more readily recognizes Fahrenheit. Next slide, please. So the Descartes Lab platform, you can kind of think of it as not so much layers of data, but as a giant repository of pixels from various sensors that can be accessed using the API. So we're using Landsat, but the repository includes NAPE and IRS and probably a couple dozen or a few dozen other kinds of remotely sensed data. And as I mentioned earlier, it has access through an API. So we write Python that takes advantage of that API. They have an extremely fast system. It's designed for fast processing. I know at one point they were advertising that they had the 5th fastest supercomputing system in the world. I don't know if that's still the case or if it was marketing, but it is very fast. And in fact, we prototyped this process before we made Descartes Labs a partner. We tried doing this just with GIS software alone. And it was pretty much undoable at the scale that we're doing it now, just because of the space required and the RAM required. And we could have broken it up and run pieces of it and probably put it together in a few months' time. But what the Descartes Labs platform has allowed us to do is to produce an initial product anyway in a few hours' time, as opposed to a few months. And as I mentioned earlier, they're headquartered a half mile from our Santa Fe office, so we just walk to meetings at their place, and they walk to meetings at our place. Next slide, please. Okay, I tried to keep this diagram as simple as possible, and I'll try and go over it step by step. And I realize this probably doesn't capture everything, but at a high level, and I'm sorry if it doesn't look high level, but I'll go through it here. So we use GeoJSONs, city boundaries, because that's the format that the Descartes Labs platform accepts. So what we have is We get the city boundaries as a shapefile from Census Bureau. So these are the official US city boundaries that Census Bureau puts out. We have to convert those to GeoJSON and reproject those to a geographic projection because that's the format and projection that Descartes Labs platform requires. Then we use the Python code to feed those GeoJSON boundaries along with processing instructions into the Descartes platform through the API. And I try to depict here the next step is that the code basically reaches down into the bucket of pixels and pulls out max values for the summer for every pixel for every city in the US. Then from those max pixels, we compute a mean of the max, and then we subtract that mean from the max to get the heat anomalies. Then the heat anomalies, so this is all done in arrays, in memory arrays up to this point. So then the heat anomaly is instantiated on our system as a GeoTIFF raster. So we pull the data out of the array, instantiate it as an on-disk raster in GeoTIFF format. For those of you that aren't familiar with raster data, it's basically just a collection of pixels, and each pixel is assigned a number, just like a digital picture. And GeoTIFF just happens to be the most popular form of geospatial raster data. So it's easiest to work with in the widest variety of platforms. And if we need to come back to this slide, or if you have questions about it, I totally understand, and that's not a problem. Okay, let's go to the next slide. So the next thing we do is take that GeoTIFF data and bring it into ArcGIS Pro. So ArcGIS Pro is Esri's flagship software. Those of you unfamiliar with Esri, it's ESRI, it's short for Environmental Systems Research Institute. They're located in Southern California. They are the first and biggest developer of geospatial software. I used to work for them for 13 years, and so I'm very familiar with their products. And basically, the process goes like this. So the first thing we do once we get the GeoTIFFs back is we trim or negative buffer for those of you that are familiar with GIS, the boundaries by about 50 meters to eliminate edge effect errors. And I won't go into edge effect errors except to say that they can be for a lot of reasons, but basically pixels on edges are more prone to errors, so we remove those. We set all values below 1 to null because values below 1 are not heat islands. They're not excess heat. One of the things we do is reclassify all of those heat anomaly values on a 1 to 5 scale to get heat severity values. And I'll talk more about reclassification in an upcoming slide. Then we create a Mosaic Dataset and add all the output rasters to it. So a Mosaic Dataset is an Esri proprietary data format that allows for fast display and processing, and I'll talk more about Mosaic Datasets and image services in the next slide. And then the Mosaic Dataset gets served through an image service. Next slide, please. So here's a depiction of how a Mosaic Dataset works. So as I mentioned, it's a Esri proprietary data structure, and this comes in really handy with the 14,000 city heat rasters that are produced, because we can serve them as one data set rather than 14,000 separate data sets. So Mosaic datasets don't contain the data, they just have pointers to the data. So they provide faster viewing and processing because they only present the user with the pixels in an area of interest rather than the whole data set, and only at a scale suitable for a view or an analysis. So at any given time, they're only presenting the user or viewer with a tiny fraction of the data, and that's why they're fast and efficient for serving data. And so this is the overall process in the diagram. So we've got our instead of 3 layers there, picture 14,000 of those raster heat data sets. A Mosaic dataset is created and pointers to those raster datasets are created. That Mosaic dataset is then served as an image service, and then an image service can be used by applications that understand image services, which includes both ArcGIS and QGIS, which is free geospatial software. And then there's several other softwares that understand and could use image services also. Let's see, next slide, please. So I mentioned that we create a heat severity layer from the actual heat anomalies. So this is based on classifying the heat anomaly rasters into 5 classes. Very low, low, moderate, high, and very high is how you would term them if you were going to take away the numbers and describe them. We do this through a Jenks natural breaks classification method. This is a well-known, well-documented, well-used classification method. Basically, it seeks to reduce the variance within classes and maximize the variance between classes. And so you can see an example here of how Atlanta is classified. So the max heat anomaly in Atlanta is 25. So there are values of 1 to 25 in Atlanta. And then you can see how when it's run through the Jenks natural breaks classification method, it gets classified. So it's pixel values 1 and 2 are very low severity. 3 and 4 are low severity, 5 through 7 are moderate, 8 through 13 is high, and 14 through 25 becomes very high. So what's the advantage of doing this? So a heat island is relative to the area to which it's being compared. So heat severity is a way to normalize the data. So no matter what the range of the data, once it's gone through the classification process, every city is broken down into classes 1 through 5. Another advantage is that breaking it down into these classes makes it very human understandable. So if I say, well, Atlanta's max heat anomaly is 25 and Burlington, Vermont's is 10, you don't really have a frame of reference. But if you normalize the data, you do. It also works well for mapping. So otherwise, cities with very high anomalies like Atlanta would dominate the map. And so this is the data that we use at TPL, and this is the data that's served in ArcGIS Online. Next slide, please. So I also said I'd mention what an image service is. So it's a web service. It serves raster data as opposed to a feature service that serves vectors, or a map service that serves map tiles. So when you see an online web map, it's not usually actually data, it's a picture of data. So it can work well for viewing in a map, but it doesn't work for geospatial analysis. And so the goal of an image service is to serve up actual data that can be further used in geospatial analysis rather than just looked at. So as I mentioned earlier, all the heat island rasters are loaded into Mosaic Dataset, serves as an image service, and this image service is reflected in the ArcGIS Online Living Atlas of the World. And as I mentioned, the image service carries the same information as the on-disk data. So the goal of this is that you don't have to download this data set and chunk out your piece. You just hook up to it and start processing. And that's a huge time saver, a huge space saver, a big advantage when you're going to take this data and do continued processing on it. And this heat island image service is running on a TPL managed server. So when you're hitting that image service and using it, you're actually pulling pixels through the service from a TPL server. Next slide, please. And I mentioned ArcGIS Online. So this is how we share the image service with the public. In the area of ArcGIS Online where the heat island data resides is called Living Atlas. And this is a repository of ready-to-use data apps and maps, and there are thousands of data layers in Living Atlas. It's one of the things that I helped start up when I was at Esri, and it's basically a library of online geospatial data curated by Esri. And it's taken a while for people to catch on to the idea of services as data rather than map services, but it is catching on, and now a lot of data from federal agencies and from other vendors is available as services now. Next slide, please. So quality analysis. So no data set containing billions of pixels, and between the heat island pixels and the null data pixels that are between them, we've got about 13 billion pixels being served in this service. So no data set containing billions of pixels is going to be 100% perfect, and this data set's no exception. So you know, you can't QC 13 billion pixels. You know, not with a staff of 11, not with a staff of 11,000. So you have to do statistical sampling. And so we took a statistically significant sample size and assessed those for quality, and found that about 1.5% of the sample contained errors. And you can see an example of the error below. It's basically discontinuities along Landsat scene boundaries caused by significantly different temperatures abutting each other. We corrected the errors that we found, but with statistical sampling, it indicates that whatever percent errors you find is the percent you'll find throughout your data set, not just in your samples. So we fully expect that it's likely that the error rate for the entire data set is also about 1.5%. So I would be amazed if you didn't find some errors in there. That said, it's for this huge of a data set, it's I consider that a fairly low error rate. Next slide, please. So applications to use the data set for. So we use it for ParkServe. So ParkServe is access to parks, and heat islands are a ranking factor. And I'll show you in another slide for schools and school districts how we've combined schools data with heat data to produce some interesting results. We're constantly finding new uses for this data. We've got a lot of things lined up. I can't really talk about yet, but we've got a lot of interesting uses coming up for the heat data. And then outside of TPL, these are the top users of the data that we've found so far outside of TPL. We've got people in academia. I'd say probably environmental consulting is the biggest user that's at least contacted us about what the data is, how it was produced, how to use it. And by the way, that data is, there's some pretty extensive metadata along with the service. So we've actually revised it in response to people's comments. So hopefully that will work for everyone here too, but if not, give us comments. And city planners are also using it. And I think that's probably just a sample, because I checked the service as of this morning, and right now we're just shy of 7,000 views in the 5 months that the data's been up. So it's been pretty popular. It's definitely getting out there. Next slide, please. So here's just a sample result for Central Phoenix. So this is just a view of heat island data in a dev version of our ParkServe app. So we're still deciding if we want to have the heat data in a public version of the app or just use the data as a ranking factor without actually showing it in the app. But this is an example, like I said, of a development version. So we are showing it, and it just shows you in this view, the red spots are hot and blue spots are cool, and every place else is in between. And so if we have an optimized park location that falls in one of the high heat areas, we will bump up the priority of that. And so if a city is thinking, well, where can we get the most bang for the buck in building a park. It could be that, well, we don't only want to just serve people recreation wise, but we also want to mitigate a heat island. You have that option to use that as a ranking factor for optimizing park location. Next slide, please. Okay, so now we just get into a few interesting facts, or at least I think are interesting, revealed by the data. So you can see that this is a map of big cities, and by big, I set a threshold of a population of 200,000, and the highest heat anomalies. So these are heat anomalies, big cities with heat anomalies of 20 degrees or more somewhere in the city. And as you can see, they're mostly in the East and Midwest, except for Salt Lake. I thought this was interesting and kind of an unexpected result. But when you think about it, we're not doing just heat, we're doing heat anomalies, so heat in relation to the rest of the city. And so I guess it's not surprising that a lot of industrial or formerly industrial cities, or cities with a lot of concrete and not much green space, show up in this map. And of the big cities, Louisville had the highest single heat anomaly, which was 27 degrees. Next slide, please. So schools and heat, we thought this was a really interesting outcome. So essentially, household income range for an area, and by area I mean census block group, very accurately predicts the heat anomaly of schools in the same area. And as you can see, there's an R² there of nearly 0.99. So essentially, a low-income household is more likely to send their kids to school in a hotter area. And we didn't really take a look into why this is the case, but it could be because a lot of low-income neighborhoods are in more industrial areas with fewer parks and green spaces. We haven't gotten to the point of analyzing too closely why this is. I'm sure other people have correlated heat and income, but this is an interesting use of the data for schools and heat islands. At least we think it's interesting. Next slide, please. So what's next? So we've got the heat severity data made public. We've had some requests to make the anomaly data public. So that's probably something that we will do. We've also had people who want to retain the 0 and negative values to show cool spaces in addition to hot spaces. So that's something that we have and we can put out. We'll have to decide if there's enough demand for that. But it's not that difficult to do. And then another thing we want to do is track how well TPL projects are mitigating heat over time. So we'd like to eventually be able to correlate, okay, this much green space correlates to this much heat reduction for an area this size, and be able to not just look back in time through NDVI, which is normalized differential vegetation index, or basically greenness index, but also be able to predict, if we want to create a park here and we also want to do some heat mitigation, what % of it needs to be green space. So those are the kind of things that we're looking at doing and would like to be able to do. And last slide. So that's basically it. That's my email if you want to contact me with questions beyond the time we have for this presentation, but I'll go ahead and take questions now.
Great, thank you so much for that presentation, Pete. This is Lad again at the University of Arizona. And for everyone that's joined us here today, just a reminder, please do use the Zoom group chat function and type your questions into the chat box, and I'll attempt to moderate those best I can. Pete, before I start with the first question that we've received, one of the things I think is exciting about this project and the service you're providing through Trust for Public Land is we did a case study analysis of cities in the Southwest in Arizona, New Mexico, and only 4 of the 44 cities that we looked at had access to an urban heat island map to even start conversations.
Oh, wow.
And the other cities, over half of them were very interested in getting the information, but most of the urban heat island maps currently are created through a partnership with the university, or they get a special grant as a one-time deal. So to kind of have this information up there is very powerful.
Yeah, thanks for that. Yeah, we've kind of been overwhelmed with the response, how many people are interested in this. So yeah, it's definitely getting out there.
Great. Well, the first question we have is this data set versus something like the Google Earth Engine.
I'm not sure. So Descartes has a lot of tools built into their API, specifically for processing the data. So not just for grabbing the data, but for making things easy. They've got a lot of built-in math that instead of dozens of lines of code are basically distilled down into a line of code. And so it's a lot, for one, it's a lot easier to write code against the Descartes API. For another thing, it's Python. And for another thing, it's just plain fast. It's just way faster.
Okay, great. Another question for you, and the questions are rolling in, so we'll get to as many as we can with the time that we have with you. Another question is, let's see, is it possible to do a temporal analysis with this data set?
Yeah, in fact, when we did the analysis of schools, we thought, well, let's go back. So Landsat 8 was launched in 2013. And so we thought, well, let's go back and grab the 2013 data and attribute schools with the 2013 data and then compare it to the 2019 data. And I didn't show it on a slide, but the 2019 data, whether it's whether it's due to climate change or just a hotter summer, did show an average increase at school locations of, I think it was 0.13 degrees. So a little over 1/10 of a degree at school locations in that amount of time. So yeah, it's definitely possible to track heat anomalies over time. Perfect. But only with Landsat 8, only as far back as 2013.
Okay, thank you. The next question is, you mentioned that TPL is looking at kind of evaluating the before and after heat mitigation efforts, and they have research colleagues working on the same question. But kind of what are your plans for that, and how might you accomplish that?
What we did so we took a sample of 32 playground projects in New York City, and basically compared, and so we made sure that none of them were before 2013. So we got 32 of them from 2013 and compared the heat anomaly values between 2013 and 2019. And what we found is that where we did significant greening, where we put in a lot of grass and trees where those areas didn't have grass and trees before, as you would expect, they were significantly cooler. But where we put in playgrounds that were completely designed for recreation, in other words, they had 100% artificial surfaces, those either stayed the same or actually even went up. And so that's an area where was a real eye opener for us, and it's changed our policy already, or it's in the process of changing our policy about how we develop parks. And whether, if recreation is the 100% concern and you don't care about heat at all, then I guess that's fine to do. But really nowadays you can't not be concerned about heat or increasing heat with a project. And so our goal now is to combine or to at least consider heat when we're creating a park, and not be a contributor to heating that area up and hopefully be a contributor to cooling it off.
Okay, thank you. We have another question related to the Landsat satellite data and data that Landsat satellites produce. How is that?
Pretty well-known couple of equations that you can get from USGS. Basically, you convert the digital number to Kelvin and then Kelvin to either Fahrenheit or it's a standard
Another
conversion
question
equation.
is, let's see here. So the question, and I'll just read it because it's a little bit long, but if you base your heat anomalies off of the max and mean values of single pixel locations throughout the summer, how do you determine, how are you determining summer, and are you using the dates or a temperature threshold? So kind of the temporal, another take on that temporal question. When are you determining?
Yeah, so it's the max value of a single pixel location compared to the mean of the max values for an entire city. So that's how the anomalies are determined. And by summer, since we're at this point, we're only working in the US, we went June 1st to September 30th. So that's how we're doing the calculation, and that's the time frame that we're getting the data from. And I should also mention that we got all the data initially from the summer of 2019, where we had errors and we kept rerunning different different time frames within the summer of 2019, and we couldn't get away from an error. We did reach back to 2018 to patch those errors basically, but so yeah, it's 99% or more 2019 data, but there is some 2018 data in there.
Okay. A question that I get a lot from planners that I work with, planners and designers across the United States looking at extreme heat, is they might have access, if they're lucky enough to have access to one urban heat island map, but they'd really like to see the change over time. So kind of that question of the mitigation impacts and using it for evaluation purposes. Do you have any plans through TPL to create like an annual update to this data set, or how feasible is something like that?
Yeah, we are planning an annual update. In fact, we're planning to update this data set in early October of next year, and in addition to updating the data that's out there, we're going to see if there's much of a call for including the other potential data that I was talking about, such as the full range of heat anomalies, or even the full range below average to zero. So we may be putting out 1, 2, or even 3 additional data sets come October.
Okay, and time for one last question. Looks like some of the participants are already downloading the data from the presentation. And the question is, it looks like it's not editable or clippable at a certain state. And so what kind of analysis do you recommend to maximize the use of the data that is available?
So you can clip it. I'm sure that there's a pixel limit. So there's a default limitation on size of the area that you can download. I'm hoping it's not, I'm pretty sure it's not smaller than the size of a big city like New York. New York was our biggest city. So it should be clippable to that extent. It's not going to be editable because it's data coming from our server and we don't want it edited, but basically how you would use it is, or how I would use it is, I would hook up to the service endpoint, bring that into a geoprocessing tool, whether that's in Arc or in Q, and set your environment variable to an area of interest. So it limits the processing to just your AOI, and that's the way I would use it. Another option is to use that same AOI to clip it out and download it, but that's kind of somewhat defeating the purpose of the service.
Okay, great. Well, thank you so much again, Pete, for the presentation. I know there were other questions that we won't have time to get to, and please do contact Pete at the email that he's providing on the screen. And just to wrap up
thank
the
you very
webinar,
much, Lad, for having me,
yeah,
and thanks for everyone who attended.
absolutely. For everyone that's still on, we have future webinars and updates at our Extreme Heat Network website at heat.arizona.edu. If you're interested in getting involved in some of the things that we're working on, please check that out and email me, lad@arizona.edu. And thanks again for joining us. And thank you again, Pete, for the excellent presentation today.
All right, thank you.